Welcome to the MAA-AMS-SIAM Judith and Gerald Porter Public Lecture. I'm Deanna Hansberger, President of the Mathematical Association of America, and I'm so happy to see so many of you here. Moon Duchin is an Associate Professor of Mathematics at Tufts University. Dr. Duchin received her bachelor's degree from Harvard and her PhD from the University of Chicago. Among her academic honors are her NSF Career Award, an MAA Distinguished Lecture, and she's a Fellow of the American Mathematical Society. Dr. Duchin's mathematical research is in geometric topology, geometric group theory, and Teichmuller theory. Last summer, she hosted a 6-week research cluster on the mathematics of polygonal billiards. But her interests in mathematics are much broader than that, and also include history, philosophy, and culture of science, gerrymandering, and civil rights. Dr. Duchin launched the Metric Geometry and Gerrymandering Group, a Boston-based team of mathematicians. This past summer, she and the group garnered much national attention. Chronicle of Higher Education, Wired, NPR, New Yorker, Quanta, Chicago Tribune, and others, for the Geometry of Redistricting Conference, a 5-day conference held at Tufts which educated people about the legal, historical, civil rights, and mathematical contexts of redistricting, then focused on developing expert witnesses who understood the mathematics applicable to gerrymandering. So many folks wanted to attend this conference that the group launched a nationwide series of workshops aimed at educating people about the applications of geometry and computing to US redistricting. I'm very excited to hear what she's learned. Please join me in welcoming Moon Duchin.
Thank you, Deanna. Okay. Hi, wow, pleasure to see you all. I'd like to talk about redistricting, and I'd like to do it on several levels. So my background's in geometry, and I got interested in this problem through thinking about shapes of voting districts. And you'll see that interest in geometry reflected throughout, but as you just heard, I think this problem is only tractable when you think about it in its political and its legal context, and when you think about the stakeholders. And I'll try to reflect that in this talk. Okay, so what we're talking about is fundamentally American democracy and how it works. And here we are, and what we have to do is take the country and divide it up. So this is one way to cut things up, but the problem of gerrymandering is partially that this is another way to cut things up. Okay, so are you going to cut up the country with a cleaver or a scalpel? And what are the implications of the ways that you draw the lines? That's my framing question. Okay, so let's set the stage by thinking about what the task is of redistricting. So I'll focus, now gerrymandering and redistricting happen for many different kinds of electoral contests, from national to very local, but I want to focus right now on federal legislative bodies. We have the Senate and the House of Representatives. Now, the Senate has 2 members per state, whether the state is very large or very small. And since the boundaries of states are fairly fixed, there's not a whole lot of gerrymandering to do there. But the House is another story. So the way it works is, at the moment, we have frozen the size of the US House at 435 representatives. And every state gets a number of representatives roughly proportional to its share of the US population. How to do the rounding turns out to be complicated, interesting, and is a story for another day. Okay, so what are the steps? Well, per constitutional guidance, we have a decennial census. Every 10 years, we count all the people, or we create a fiction that's called Counting All of the People. And one's coming up in 2020. This is a very big deal, and I hope that one thing I can do is talk a little bit about why the stakes of the next census are so high. Once we have our counting fiction, then we apportion representatives to the House to the states, to the various states. And then once we've done that, we have to draw lines within the states. So we need to partition each state into an appropriate number of seats. Right now, California, for example, has 53 representatives, Massachusetts has 9, and the numbers change when a new census drops. But here's the peculiarity of American democracy that makes us almost unique in the world when it comes to the combination of factors here. Officials, in this case state legislatures, tend to set the boundary lines for their own elections. And I think that's probably, obviously, setting up incentives for some problematic outcomes. And so really there's a fourth piece of the story, and that is litigation, right? Which we can expect regularly after every new map is produced. Okay, so if I want to talk about how redistricting works and what the rules are, and then how the rules are stretched and sometimes abused, we need to set out the norms and the principles. So there are many. It's not a neat list. But I would identify 6 most important fundamental so-called traditional districting principles, and then there's a variety of other norms to keep in mind. First, equal population. This is the rule that's taken most literally, precisely, and seriously. And that's, of course, about the number of people in each district. One thing to keep in mind is this is the number of people that the census locates. It's not the number of eligible voters, it's not the number of citizens, it's the number of residents counted by the census. That has to be equalized. And then the piece that a geometer loves or loves to hate, a principle called compactness, which does not mean what topologists think it means in this context. In fact, it's something very fuzzy that just means that the shapes of the districts should be somehow reasonable. And I want to spend a good portion of this talk making sense of that and trying to think about how to operationalize this idea that districts should have nice shapes. And then another one, also shaped a little less controversial, contiguity. So a mathematician would say we want our districts to be connected and simply connected. Okay, we want the districts to be a single piece and not broken up into multiple pieces. Now, if this were it, if this were the whole story, mathematicians could take it from here and be done. Okay, so this is an image from a recent paper. It got posted to the archive within the last few months, in which a team of computer scientists said, we know how to handle those rules. We can do, what you're seeing here is a modified Voronoi diagram called a power diagram. We can produce a pretty good, nice-looking map with equal population and contiguity. We can get a computer to do that. But one of the things, maybe the main point that I'd like to emphasize today is that the problem of redistricting isn't only about these mathematical sounding principles. There are more. Okay, so in particular, here are 3 more that I think are fairly universal and very important. Respect for county and city boundaries. So that says you shouldn't cut up a county unless and until you have to, and then don't do it too much. Still fuzzy, right? And that's a problem with a lot of these rules. You want fuzzy? Here you go. Next up, respect for what are called communities of interest. And so that means if you have a natural community of people who have a shared interest, you should try to keep them together. With all of these principles, I hope we're asking ourselves as we go, what's the reason for that? How does that connect to things we care about in representative democracy? And in this case, it would be that people who are kept together in a district can more effectively advocate with their representative to get their interests minded at the federal level. Okay, and then last on my list of 6, but by no means least, is compliance with a very important piece of legislation, the Voting Rights Act of 1965. So the Voting Rights Act tells us something about fairness to racial minorities. In later years, it was expanded to cover language minorities as well. And it's a very powerful piece of legislation. It was initially supposed to expire within 5 years, but it's been continually renewed, expanded, clarified, and it's the biggest tool that we have for reining in gerrymandering abuses, but it comes with some baggage, and let's take a look at how it plays out. Okay, so I identify these as the 6 most important, but there are many more kinds of principles. Some of them are reflected in state constitutions or in statute, and some of them just understood by people on the ground. And so here are some questions you can ask yourself. Other possible norms or goals that we could have when we redistrict. Maybe we're interested in some kind of proportionality. If one party, say, gets a certain percent of the vote, they should get something like that percent of the seats. You might want to favor competitiveness, and some states have written that into law, Arizona in particular. Responsiveness, you might want, when the voting patterns of people change, you might want to be sure that that's reflected in the composition of the legislative body. Or by contrast, stability. Maybe you don't want big swings in the body to match changes of mood in the public. And maybe what you care most about is a voice for the marginalized. There are all kinds of possible concerns that you can bring to the table. And to a mathematician, it should be pretty clear that they come with tensions and trade-offs. Okay, so figuring out how to make sense of these and how to prioritize these is hard, it's vague, and it's right at the center of debates about redistricting. Okay, so when it comes to gerrymandering, we tend to think about a zoo of bad shapes. So let's take a moment and visit the zoo. Let's start here with the original gerrymander. So this picture, probably well known to many of you, is from a political cartoon from 1812 in which a district in Massachusetts, this is in the North Shore of Boston, in fact, voila, there's Tufts right there, roughly to scale. So then Governor Elbridge Gerry had approved this particular voting district. It's designed to favor one political party, the Democratic Republicans, that is one party at the time, over the competing Federalists. In order to make the point that this was abusive or unnatural, what you see here in the cartoon is claws and fangs and wings, satirizing the shape of this district as some sort of menacing reptile. So this came to be known as Gerry's Salamander, which is what gave us the word gerrymander. Okay, let me show you some of my favorites. This is the notorious Illinois 4th District, sometimes called the earmuffs. Maybe you can see why. You can see from the picture that it's got 2 sort of masses that are strung together to keep it contiguous. And if you know Chicago, these are chunks of Pilsen, which is a Mexican-American neighborhood in the south part, with Humboldt Park to the north. Humboldt Park has a heavily Puerto Rican population, and they're strung together along a highway. Okay, so what's the outcome? Luis Gutierrez has won 13 straight elections to represent the 4th District, never with less than 75% of the vote, and often unopposed. Okay, so this looks like an example of one of the key tools of the gerrymanderer, something that's called packing. Okay, so packing is when you take the other group, whatever kind of group that might be, the group whose influence you want to minimize. And packing is when you stuff them into a small number of districts in very high percentages, which in effect wastes votes, right? If you have 88% voting for Luis Gutierrez, which has happened in some years, that's, in this case, maybe lots of Latino voters who could have had an influence in neighboring districts, but are instead over-concentrated into one. But the story gets more complicated from there, because this was actually a well-meaning gerrymander. So this district was drawn, in fact, by civil rights advocates in order to create, on one hand, a Latino opportunity district, but on the other hand, not to sacrifice 3 nearby majority black districts. And it was the thought at the time of drawing this that you had to give up nice shapes in order to make all those things happen at once. Okay, so this turns out to be a case of accidental or friendly packing. And that's what I want to do in each of these instances, is take the story and maybe try to nuance a little bit and indicate that each funny-looking animal in the zoo tends to have a story. Here's Florida's fifth. It's not so attractive. It was created in this form after the 1990 census, and it looked like this only for a short time, from 2013 to 2017 when it was thrown out. It wanders around in the vicinity of Disney World, picking up pockets of black population as it winds, and a bigger chunk of Jacksonville. So it's constructed in a sense to elect, to make it possible to elect a candidate of choice for the black community. And that's the language of the Voting Rights Act, the opportunity to elect a candidate of choice. But again, it seems to overdo it, creating landslide conditions, so it's had roughly 65-35 races in those years. But interestingly, the court decision in which this was found to be a packed district was loudly protested by its sitting representative and by the Congressional Black Caucus, so this indicates a little bit of tension in priorities. Yes, we know this one, Maryland's third. I hope you're all rooting for your favorite districts to come up in the list. So Maryland is arguably the only Democratic congressional gerrymander going on at the moment, and the Supreme Court will be talking about it this season. This is a plan drawn by Democrats, opposed by civil rights and good governance groups. What happened was that it pushed out a 10-term Republican incumbent by changing the demographic composition of the district, and worked quite effectively at that. And here's a great quote that I wanted to share about this. So the Secretary of State who was in charge of this redistricting said, "We didn't mean for this district to look like it does. That's just how the numbers worked out." It's a very complex situation. I mean, he's right about that. And population is the #1 driving characteristic. All of our congressional districts don't deviate by more than one person, by which he means they've taken that dictum that you should equalize population and taken it down to the #1, right? So, yeah, let's just think for a moment about whether we find it plausible that getting the population exactly right drove this shape. Okay, Pennsylvania 7. This is a well-known district that sometimes goes by the nickname Goofy Kicking Donald Duck. One thing I love about the shape of this district is that if you look at it, it's only got this one sort of tame geometric feature, and that's a part of a circle, but it turns out that's just the state border with Delaware. Okay, so what's going on here? It's winding through the suburbs of Philadelphia, just sort of willy-nilly through the demographics, through the communities of interest, to make a narrowly Republican district. It ends up being 88% white, and it neatly avoids black neighborhoods to its east side. There are 2 different places in this map where you can disconnect the district with a single building. Okay, here they are. In one case, you can't read that, but a hospital. And in the other case, it's a seafood restaurant, whose electoral significance is unknown to me. And then we have our star, North Carolina 12, probably the most litigated congressional district in history. The classic, the notorious, the district that launched 1,000 lawsuits. In particular, Shaw v. Reno, a really important Supreme Court case in 1993, which was the first of a string of court cases that's sometimes called the Shaw line of cases, in which the court acted confused about shape and its significance for redistricting. But what happened over and over is that districts did get thrown out on the basis of shape. And the language that's used in these decisions is really interesting. Shapes are derided as bizarre, tortured, eccentric, and thrown out partly for that reason. On the other hand, the justices complain that they don't want to be in the business of deciding what is prettier than what. And the language that they use in the decision is, we do not want endless beauty contests when it comes to congressional districts. This one was created in this form after the 1990 census, and it was sort of offered up or defended as a voting rights district. What it does is slices black population out of 3 cities in North Carolina, create something that at the time had a narrow majority of African Americans. But here I want to emphasize something. So this was originally drawn by Democrats and later kind of reformed by Republicans. What's happening here on both sides is that race is being used as a proxy for party. So by ostensibly following the guidance of the Voting Rights Act, what's happening here is partisan gamesmanship. And something that I think is very important is to remember that democracy works best when we respect the agency of voters and don't simply use them as pawns in a game like this. And much too often, as you've heard throughout my tour of the zoo, race has been used in exactly that way by the people drawing the lines. And here, let me pause and say, if this is the most that you've heard about racial justice in a math lecture, I'd like to use this opportunity to hope that it won't be the last or the most. I think it's something that we as a community have the tools and the ability, and I really think the interest to be better engaged with. Okay, so we saw some ugly, and now we want to think about how ugly, okay? We want to think a little bit about what's going on with these shapes. So let me introduce some scores and some metrics for getting our hands on the question, the thing the Supreme Court was so worried about, getting away from the beauty contest, right? And trying to figure out what kinds of shapes are at least red flags for abusive practices. Okay, so if you stop a mathematician and you ask, how would you delineate what shapes are bad shapes? I believe this is the first thing you'll most likely hear, the Isoparametric Theorem. It's been known or guessed since antiquity, and the theorem basically says, if you compare area to perimeter, if you try to enclose the most area with a given perimeter, circles are the way to go. And I see the pi got dropped from my slide, but there's pi there. So the Isoparametric Theorem says, if you have a bounded open subset of the plane, whose boundary is a rectifiable curve, then the length and the area, the boundary length and the area, compare by this inequality. 4 pi times the area is less than or equal to perimeter squared, with equality only for circles. And there I have some fine print about what I mean by area and perimeter. Okay, and this gives rise to a score in the political science literature for voting districts called the Polsby-Popper score. This is the one that comes up most in court cases when people are trying to get their hands on what compactness actually means. Again, there's a missing pi. So if we take 4 pi area over perimeter squared, then it's immediate from the isoparametric inequality that you get a score here that varies from 0 to 1. And so a high score, a high Polsby-Popper score means you're nice and plump, roundish. And a low score probably means you have wild tentacles and skinny bits. Okay, so this is just a red flag for various kinds of bad shape. Sometimes people have objected to the pi looks funny there, or to the fact that this is sort of organized around circles. So I just want to point out what's possibly obvious, which is there are other ways to normalize this. We can do the iso-squaremetric version, where we have factor 16 here rigged to make this come out to 1 when you plug in a square. One thing I've learned from the political science literature is that cosmetic variants like this often go under whole different names and get listed separately in expert reports. Of course, these aren't meaningful variants, but they help us think about it maybe in different ways. Okay, so what this lets you do is take a range of voting districts and kind of organize them. It gives you a quantified way to organize how maybe reasonable and efficient the shapes look. And so we have here a few districts. This one's in Indiana, and it looks pretty square. It's gonna score high iso-squaremetrically. Here's one from Michigan. This is Massachusetts 7, which contains the front door of the Tufts math department. And next to it, the back door of the Tufts math department. Yeah, so our math department is actually split between 2 voting districts. And then we have the Pennsylvania Disney abomination there, again, at the end. So this seems to do something of what we want. It gives us a way to numerically organize our feelings about shapes and how reasonable they are. But there are many more. And actually, this is part of the problem. In the political science literature, I've counted at least 35 different scores that people could use for compactness. And this is an obstacle to court adoption of any one. because there are different scores and they work a little bit differently. So let's look at some other things you could do. Some scores look at skew. So you can measure kind of how elongated something is by various ways of taking a ratio of short axis to long axis. So for instance, a thing you could do is the two farthest apart points in your district, and then some perpendicular cross-section to that that's maybe as long as possible, and you could take the ratio of those and call that your skew score. But there are lots of other things you could do. Take the same district and choose some kind of bounding rectangle for it. Here's the XY parallel rectangle, or you can just look all around for the rectangle with the most extreme ratio of length to width, and that's another score in the literature. It's another skew score for your district. Okay, another thing you could think about is indentedness. The area of the region divided by the area of some kind of comparison figure. So a natural way to do this would be take your district and look at its rubber banding closure or its convex hull. And then ask, what is the area of the district divided by the area of its convex hull? So that's kind of penalizing it for indentedness, if you see what I'm saying. But you could do it just as well with a bounding rectangle. And in fact, the second most popular score in court documents is this one. It's called the Rioch score, and it compares the area of the district to its circumscribing circle. I wondered for a long time why this one got so popular. Why would the circle be the way to go? And it turns out, and this is, I think, a really telling story, that Maptitude, which is the industry standard software people use to do redistricting, figured out how to code this Rioch score so you could just assess it with a single button push. And it was the fact that it was built into the software that caused this really strange and hard to defend score to catch on so much and make its way into all the court documents. And I think that's a fascinating story of all the interplay between technology and logic. Okay, so let's make a quick observation about the last two ideas, this skew score and this indentedness. Notice that skew and convex hull, they both have what I want to think of as blind spots, but they're complementary blind spots. Convex hull doesn't mind a really long, skinny rectangle because that's convex, and it says, yes, I like that. It's not indented at all. On the other hand, skew would give a perfect score to a square that's carved out like a Swiss cheese or maybe some sort of Sierpinski crazy fractal. As long as the bounding box looks nice and equally proportioned, skew is going to give that a good score. And we probably think neither of those is a great voting district. So just a quick idea, since they're complementary blind spots, maybe we can combine them. And a thing you could do is create something that I've dubbed a box score that just adds the two. So if one score likes this too much and the other score likes this too much, when I add them, neither one of those shapes can hide. Right? So that's the idea. And what I hope this also illustrates is just how easy it is for these compactness scores to proliferate. Right? And it's fun. We're mathematicians. We can think of new things when we do this, but that's not necessarily what's really called for. Instead, we need to be coming back to that question, how does this have anything to do with the features of a representative democracy that we want to promote and preserve? Okay, I'll mention one more, which is dispersion, which I think is a very natural idea. It asks, how spread out or sprawling is your district? So you can make sense of that with an average distance between points in a domain or some kind of moment of inertia if you think about it in a physics way. So just a quick note, if you actually sit down and do a little calculation, what you'll see is if you do this kind of averaging, like an L2 kind of averaging, and you do Euclidean distance between points, then if you look at the average distance between pairs of points in a domain, that turns out to be the same thing as the average distance of a single point to the center of the domain. Nice fact. But if you change your averaging or you change your metric, this fact goes away and you have choices to make. Okay, and you might think it's better to do a discrete or even a finite version, since after all, there are a lot of people, but a finite number. And so you can instead take the average distance between voters or from voters to a district center. I think this is a sort of appealing one, particularly if you imagine replacing distance with travel time, because you get to think of it this way. People used to say, how long would it take the representative to visit the whole district? But I like to say, how long does it take you to go yell at your representative, right? Okay, for all of these, quick note for the mini mathematically minded, it's really important to normalize for size. Back when we were doing isoperimetry, area versus perimeter squared, that's why we squared the perimeter, so that we get something that's scale invariant. And we want to do the same kind of thing with dispersion. So here's a fun little brain teaser for us. I have one district here in pinkish purple that's round, and another imaginary district that's a square. Which one is more compact from the point of view of dispersion? In other words, which one has less average distance between its points? Well, probably you're gonna guess. Any guesses? Which is better? Does anyone like the square? One hand, two hands for the square. Okay, so here's what happens. Look, the square's better. Surprise. So if you ask yourself how that distance compares to d, the diameter, or the longest distance in the district, then the square actually has a smaller coefficient than the disk. Okay, so that's saying somehow the square is better. And this might offend your intuition, perhaps, if you're a mathematician, but that's because we've maybe normalized this wrong, right? What's going on here is the square has this long diameter. In the circle, all the diameters have the same length. You might say that's the definition of a circle. But the square has this long diameter, so if we make that the normalization factor, the square is going to look better. To try to illustrate that, imagine that you add some like long, skinny antennas to your square, right? What have you done? Well, you've driven up the diameter, if you make them very long, and so you've made that coefficient look a little better, but there's no mass in those long antennas, so somehow this isn't maybe capturing the right thing. So instead, what you might want to do is normalize by the square root of area instead of by the diameter, and then you get the theorem that maybe some of you were expecting, which is that circles are best. Okay, so just another idea among the many for how to get our hands on what it means to be a good or a bad shape. So with that in mind, let's come back to the framing question, compactness, but why? Okay, so here we want to ask ourselves, what is it that compactness is capturing? And that might help us decide which of these scores do a better job than others. Okay, so let's think about what compactness is good for. How do compactness considerations help promote fairness, fair redistricting? Well, I think there are two main arguments for why to use compactness. And one is, and they're both really good reasons, in my opinion. So one is any constraints on shape, or in fact, any constraints at all, limit the power of the map drawer. So something I want us to keep in mind, and it's really important for this problem, is just how many ways there are to draw a map. Okay, so currently, congressional districts have about 710,000 people in them. And then you take a state, which has many millions of people, and you need to partition it into a certain number of pieces that have 700,000. Do a little quick math and you'll see the number of possibilities. I like to say it's not astronomical, it's bigger, right? It's bigger than space data, it's huge. And so, the map drawer a priori has an enormous amount of power and discretion to make designer districts that have whatever kind of outcomes they might be wanting to promote. And so argument number one is that shape constraints limit that power a little bit, and possibly in a salutary way. This is compatible with but distinct from explanation number two, which is that to do really extreme gerrymandering, you can only do that if you allow the shapes to get bad. Okay? And for this point, I want to emphasize any agenda that you have, whether it's a positive agenda or a nefarious agenda, any agenda that you have, if you want to take it to a very extreme place, that's what I mean here. You're going to have to sacrifice shape in order to compose carefully the people in the district. So let's work through these ideas with an example. I want to try to convince you that both of these ideas have some merit. Namely, I want to try to convince you that, that compactness will detect gerrymandering. So let's look at a toy example. Here it is. It's a 10 by 10 grid. And let's cut it up. And let's say our task is to district this square into 10 districts of 10 squares each. We're going to chop the big 100 squares up that way. Should we cut it like this? Should we cut it like this? Should we cut it like this? How do we feel? And what's the likelihood that each of these is trying to advance an agenda? Right at this point, I want to say, we are right now in no position to know which of these is most fair because all we're seeing is the shapes and not the underlying demographics. Okay, so now let's take these pictures and look at where the voters are underneath them and use them to think about the characteristics of these 3 different plans. Okay, so here's the grid. It's a 10 by 10 grid. So there are 100 squares and 40 of them are orange. Okay, so I have 40% orange voters in my toy example. So since I'm cutting it into 10 districts, probably we expect that orange should win 4 seats. 40% of the voters should become 40% of the representatives. Maybe we think that would be fair. And now I want to show you that's kind of hard to do. Okay, so that first plan, I'm going to call it Plan A, looks like this when it's overlaid on those voters. And let's actually rotate it a little bit to Plan B. And now let me make a quick point. Exact same underlying shapes, right? But it's going to have a really different, right? It's going to have a really different property as a map. Here's C, and then here's D. And now I think you can see D is kind of rigged with an eye to where the people are. Well, what does that produce? If you count, what you'll see is that this map produces 2 safe orange seats and 1 toss-up. Remember, the maybe naive expectation is 4 orange seats. This plan has no safe orange seats at all, but 3 toss-ups. This plan has 4 safe orange seats and no more that are easily gotten. And here's a nice gerrymander for you. This plan is custom designed to have 6 safe orange seats. I've turned 40% of the votes into 60% of the representation. This gerrymander is brought to you by packing and cracking. So I mentioned packing before. That's when you stuff the opposition into a small number of districts, and you can see packing happening here. Pink's been packed. But the counterpart strategy is cracking, which is when you take opposition voters and you disperse them into several districts. Even though they could have prevailed in a voting district, you spread them out so that they're in numbers just a little too small to get any representation. Okay, so the most gerrymandered maps of all have both packing and cracking going on at the same time. Okay, so then I can go back through these maps and I can tabulate some different compactness scores. Here's my 16A over p squared, my box score, my convex hull. This is an average moment of inertia, so it's a dispersion score there at the end. And at the beginning, I just put the total perimeter, just added up the perimeters of all the districts. Okay, so it's a very naive measure of how eccentric the districts are. And of course, as we heard before, B will score no differently because it's built out of the same shapes. C changes a little, D changes a little, and here's a summary. Does it work? Surprisingly, perhaps surprisingly, it seems to work in the sense that maps AB and map C, it's not clear to these compactness scores which of those is preferable. The 2x5 rectangles or those Tetris-looking shapes, we're not sure which the compactness scores like better, but we're very clear on how we feel about D, the extreme gerrymander. That's not a cherry-picked example. It's actually quite hard to make a map where D gets 6 seats, and I'll talk a little bit more about how to measure how difficult that is. So the bottom line here is you actually can't get 6 seats for the Orange Party without red flags across all this whole range of compactness scores. Okay, so that's a small, but I hope persuasive indication that the compactness scores do something to constrain the most extreme outcomes. Okay, so as I mentioned, every mathematician, I think, will look at this and try to think up their own scores, right? I certainly did. So let me take a quick moment and tell you about what I think is a fun new idea. It's a current project that I'm working on with combinatorialist Bridget Tenner. And so this is just one of all kinds of possible new compactness ideas. And our idea is discretize your geometry, or as the slide would have it, what would a geometric group theorist do? Okay, so what we want to do here is take coarse or discrete definitions of area and perimeter. So the way I'll make sense of that is like this. So I have these units of census data. The census comes to us in pieces called census blocks, block groups, or tracts, or we can take a state and just think about it in terms of its voting precincts. And I can build my redistricting plan out of those pieces. Well, one way to approach this is to put down a graph with a node for every piece and edges when two pieces are adjacent. So I want you to imagine these pictures as grids of precincts in a state. And later I'll show you an actual picture of what that might look like in a particular state. But this slide is to tell you about discrete area and perimeter. So here's what I'll do. So imagine my voting district is the colored dots here. Then the area will just be the number of dots. In other words, the number of, let's say, census tracts in the district. And I'll call them perimeter if they're on the boundary. Very simple idea. I think we can agree, I hope. And then armed with that new definition of area and perimeter, I can now take area and compare it to perimeter squared. So first let me do that in this square grid. If I have an n by n square, its area will be n squared. Is this clear? Does everyone understand what I'm saying? Can you weep loudly if you don't understand what I'm saying? Okay. And the perimeter is 4n minus 4. So something nice happens as you zoom out asymptotically, and here's the geometric group theorist in me wanting to think about how to make sense of these numbers. The ratio, area to perimeter squared, stabilizes nicely. It tends to a limit. So as you refine the graph, you're stabilizing to a certain score. On the other hand, I've drawn a hexagonal district in a triangular grid over here, and I get a different formula for the area, a different formula for the perimeter, and I still get a limit. It's a different limit, but I still get a limit for how area scales against perimeter squared. So the point of that is to say this behaves well under refinement if the pattern is stable. Okay? Of course, not every voting district is like a lattice, but it is actually an empirical fact that the geometry of voting districts is surprising. The dual graph to census data has surprisingly regular geometry. Okay, so what we want to do with this is take discrete area divided by discrete perimeter squared and call that a new score. And I think we've convinced the folks at Maptitude to build it into their next release. So maybe it'll catch on. And then let me just take a second because I think this is interesting in terms of the interplay between the math and what we're trying to get the math to do for us. What's the work that we want it to do for us? Classical Polsby-Popper is subject to all kinds of bugs and flaws and paradoxes. One example is the coastline paradox. Okay, so we know the chestnut about the coast of England that says the length of the coast of England depends on the size of your ruler, right? In other words, it depends on the resolution if you want to think about it in computer terms. And the more you zoom in and the more detail you can see, the more perimeter you'll measure if you have something that's fundamentally fractal, which coasts seem to be. So the coastline paradox here is that the classical compactness score, area over perimeter squared, can actually change when you zoom in, and that seems really awkward, right? Empty space effects. So a Great Lake, right, or just say some big body of water. Classical Polsby-Popper really cares whether that's assigned to this district or to that one, because it makes a big contribution to the area. But there are no people there, or very few. Actually, I learned that the Charles River is a census block, population 12. I don't know who they are, but so that's what I'm calling empty space effects. And classical Polsby-Popper is even sensitive to map projection, like the world is round and we need to flatten it out. And how we do that changes this score. But it's not politically meaningful, right? And so discrete Polsby-Popper, our little intervention here, it corrects for some of these effects because it's really just tuned to the actual population and where the people are. What we found, and I think this is very promising, is that relative rankings are quite stable as you change the units. So here's a picture that shows, remember the earmuffs, Illinois 4? Here I've shown it broken down, overlaid on a map of census tracts, block groups, and blocks. These are the three different levels, sizes of census data. Everybody with me? Okay, so for each of these I can count the number of chunks that are along the boundary versus the total number of chunks, and that's how I build my score. And you can see from these pictures that the score will change when you change the units. But what our fingers were crossed for and what actually seems to work out is that the way the 435 congressional districts are ranked relative to each other is fairly stable when you change the size. And that is a really positive indication that this is picking up something meaningful. Okay, and then finally I want to say something that I think is also apparent from these pictures. A critique you can have of the classical Polsby popper is that not only is it seeing irrelevant stuff like coastlines and lakes, it's not seeing important stuff. It's not seeing where population is dense, where communities are clustered. It's not seeing the people. And so I think the real selling point of this idea is that the analog of a coastline in discrete Polsby popper world is a line that cuts through the middle of a city. That's the thing that blows up when you zoom. Okay, so I think that's quite interesting, and it bolsters the argument that this score is much better tuned to the stuff you should care about when you redistrict. Okay, so those are metrics, and metrics are nice, but I want to close by talking about something bigger. I want to talk about not metrics, but methods. What do we do with these metrics, right? And there I think there's some really fascinating momentum and progress and lots of good stuff to talk about. You may have noticed some news stories. So the anti-gerrymandering movement has had favorable court decisions in the last month in Pennsylvania and just in the last few days in North Carolina. There's also this giant Supreme Court decision coming up on Wisconsin that could come as soon as next month. There's that picture you might have seen in the New York Times of North Carolina legislators talking about possible lines. Okay, so what happened here? This district court in North Carolina just a few days ago threw out the current map as a partisan gerrymander. This is a very big deal because throughout US history, we have never found a way that pleases the Supreme Court of deciding what kind of partisan advantage is too much, right? And so we have no control. We have the Voting Rights Act to control racial gerrymanders, but we've been without tools to flag, recognize, and rein in partisan gerrymanders. So this case is a big deal, and you won't be surprised to hear that the North Carolina legislature is very grumpy about this decision. So here's the chairman of the Republican Party in North Carolina complaining about this decision. He says, I love this, a gerrymander is by definition and common understanding a strange-looking monster drawing. The context of this quote is this. North Carolina's had its districts thrown out over and over again, and they've been told, go back to the drawing board, draw us new districts. And we had a mid-decade redistricting that took very, very ugly districts and made them look much nicer without changing their bottom line. Okay, so it's, it's about as extreme of a partisan gerrymander as you can possibly make in the state. But this gentleman, Robin Hayes, is crying foul because he's saying they don't look so bad, and that's what gerrymandering is, right? So PolitiFact rated this mostly false, and here's the quote that goes with that verdict in part. These days, with incredibly rich data available to the line drawers, very skewed districts no longer have to look like exotic reptiles with fangs and claws. Okay, so maybe we think this person just doesn't understand the geometry. Okay, but that was me. And by the way, I have to say, as a geometric topologist, it is so cool to be in PolitiFact's Rolodex now. That's really a nice perk of this work. But I strongly believe this. So if I spent a lot of time today talking about compactness metrics, and I think compactness can be an important part of the story, but the name of the slide is compactness alone won't save us. The more we know about people, and the more stable their preferences, the easier it is to make abusive districts that don't look so bad. Okay, so we need new techniques, and the good news is we're getting new techniques. Okay, so this slide's called How Extreme is Your Gerrymander? So I can tell you firsthand, because I drew it, that example from a few slides ago, where orange got its 6 seats out of 10, was hard to find. It took a long time and many thrown out, wadded up pieces of paper to actually get that advantage for orange, even in my really simple 100 voter model. And a computer can be used to actually get a handle on just how hard it is to make a really extreme map. So here's an image from the working group of Jonathan Mattingly at Duke that shows a random walk in the space of districting plans. And I'll spend the next slide or two telling you how that goes, and many of us really think that a scientific consensus is emerging around this idea, that you really want, the space of possibilities is just too big, and you really want some sophisticated computational help exploring it. Okay, so what I did here is a quick Python run, and I want to thank Christy Graves, a grad student at Princeton, for the Python code to do this. A quick run trying to take that map I showed you before and look at all the different ways of breaking it up, and looking at how many seats you would get. And this, to me, was a really surprising outcome. Even though orange had 40% of the votes, in less than 1% of the possibilities did it get 40% of the seats. Okay, proportionality is actually harder than you think. Even proportionality requires you to do what you might call some gerrymandering. Yeah, let's look at that in more detail. So what I'm showing you here is the outcome, the histogram, of the different number of seats that you can get when you start with a particular map and just flip it randomly 100,000 times. And what you'll notice if you can read the labels is that 2 or 2.5 seats seems to come up the most often. Okay, but maybe that was just a quirky run, so let's do another run. Oh, that looks pretty similar. Okay, let's do another run. It's a little different, but qualitatively pretty similar. And maybe that makes you ask a few questions. Questions you should ask. Questions like, if I'm sampling, if I'm random walking around the space, how do I know that I'm seeing everything? How do I know that I'm mixing, that I'm doing a good job of understanding the full world of all the possibilities? And how sensitive is this to the choice of starting point? Right? Maybe if I started somewhere else and just ran it for longer, I'd get something totally different. Okay, so these maps were made by starting with B, which was a map that gave 0 seats to orange. So maybe if I just started with a map more favorable to orange, but no. This one starts with the 6-seat map. And I think you'll find that it looks qualitatively quite similar to the other, which I think is interesting. This is just heuristic evidence that I'm doing a decent job of understanding the world of possibilities, but I still think it's fairly striking. And let's zoom in on the maps most advantageous to Team Orange. So what you see here is to get 4, 4.5, 5, 5.5, or 6 seats. All of these runs just don't see that happen very, very often. The 6-seat outcome, you can't even see. It's there, but you can't even see it. And if you actually look at the numbers, you'll see actually getting 6 seats. In one of the maps where I started with 6 seats, no other maps had that. The only one it found with 6 seats was the one I gave it. Okay, so this is a way of making sense of the idea that an extreme gerrymander is hard to make. Okay, this is required here. Caution, handle with care. So what I want to say here, because I do think this is the way forward in adjudicating gerrymandering, what I want to say is that much work needs to be done here. Work to understand how these algorithms are operating, to sort of benchmark how good of a job they're doing, to make sure they're sophisticated, and never to use them to propose a map. Okay, so these methods are blind to all kinds of facts on the ground about the stakeholders and the people and how they're organized and all that stuff that we really care about. The way I'm proposing to use these histograms, these ensembles of maps, is not you must, oops, you know, what's next indeed, is not to say that you must pick something from the fat part of a curve. That would really be an abuse of these kinds of maps. It's to introduce the possibility of an outlier analysis. It's to tell us what I hope will be the thing that the courts settle on as the standard going forward, which is what's impermissible is an extreme outlier. It gives us a way to measure how much advantage was squeezed out of the power of drawing the lines. Okay, and so to wrap up, let me just tell you what I think is to do here. There's a lot to do, and the math is beautiful. It's really, it feels very fortunate that a problem that's so timely and a problem that, you know, where the problems are just staring us in the face and that a lot of us want to get up and do something, happens to be shot through with every kind of gorgeous math you could want. Okay, so let me say a little bit about what some of those look like. Here's a big one. This is the graph of the whole US. These are the census tracts of the whole US, shown in a kind of dual graph. And task 1, apply some network science to do some graph theory to this graph. and try to understand it better. There's a lot to do there. Network science is a burgeoning area of applied math, and so far, I don't think it's been done at all on census data, which is sort of remarkable. So there's work to be done. But next, geometry and topology. So what I have here is study the geometry and topology of the space of districting plans. So I like to call this the moduli space of metric partitions. That's asking the question, look at that universe of possibilities, and some are close to others in the sense that you only have to make a few flips in a random walk, and then some take many, many, many flips, and maybe that space isn't connected at all. Maybe there are some two maps where you can't get from one to the other, no matter how long you run. This ties beautifully in with a really exciting area of applied topology, the topology of configuration spaces. For instance, there's beautiful work on configuration spaces of disks and of hexagons, and we should be leveraging that to try to understand the world of possibilities for districting plans. So there's a kind of energy landscape the idea is to search that and see what we can find and try not to get stuck in hills or in valleys. Of course, work on the sampling algorithms, that's important. And so Markov chain Monte Carlo, or MCMC, is the kind of industry standard here. But there's beautiful ideas in math and physics, the study of glasses, spin glasses, where you're trying to understand phenomena that help you get stuck and how to get unstuck, in brief. And then last but really not least, and here's where I really want to assert that your favorite kind of math helps here, because every kind of math that I can think of has a way of cutting things up. We like to partition, right? That's one of the things we do. And so curvature, spectral geometry, and nodal decompositions, min-cut, kind of Cheeger constant, power diagrams, ideas from every corner of the math world can be used to split things up. Those will never be the maps that we introduce in legislatures, but maybe they can at least be seeds for our samplers. They can be starting points that help us better understand this vast universe of possibilities. There's an example of that power diagram. It's not going to be the way we cut up California, but we can start our exploration from that point and see what we find. Okay, and so with that, let me tell you a little bit about the efforts going forward of my group and how, if you'd like, you can get involved. So we have a website up here, sites.tufts.edu/gerrymander. I like to think we're the grinder of redistricting. And as you heard, we have regional workshops happening around the country. There are 2 of them left. There's one coming up in just a few weeks in Texas, in Austin, where we will be running a big, open to the public, free training session on how to make these maps. We're working with the Travis County Clerk's office, and it's going to be pretty amazing. The Maptitude people are coming, and the District Builder people are coming. And if you ever wanted to be a citizen redistrictor, this is a good place to come and sharpen your skills. And I want to advertise that we're doing, after that we'll be in San Francisco at the University of San Francisco, where we'll be doing teacher training, a hackathon, expert witness training, lots of ways to get involved. And gerrydata.org, that's our summer program. We're running something this summer called the Voting Rights Data Institute, where we're bringing 40 students together for 6 weeks to roll up your sleeves, do some coding, and get to know the data, and get everything ready to be able, our goal, and I'm going on the record now saying we're going to do this, I want to have ensembles of districting plans ready in all 50 states within 2 weeks of the census data drop. That's the plan, okay? What? Want to be part of that? I hope that you, for the students that are here, that you'll consider it, and for the teachers that are here, that you'll send students our way. And so with that, thank you.
Thank you, Moon, for that very nice talk. We do have a few minutes that we can ask questions. If I see that Moon is your hero, that's good to know. And we would like to see, are there any questions in the audience? Yeah.
What happens when you have a district that completely surrounds another district? Is that legal? And how do the ordinary ways of measuring in these districts come into play?
Okay, great. So I guess everyone can hear that. So the question was, can one district totally surround another? Very few states have an explicit rule against that. Some do, and in some states it's called being whole free. We want to say simply connected, right? But they call it whole free. But what I would say is you're very rarely going to see that scenario. It does happen. There are cases. But because there's so much pressure to defend your plan and because that's such an easy thing to make fun of, so I actually want to emphasize the importance of that. Right? The original term gerrymander comes from a satire that was intended to shame, right? And so I think public pressure actually and attention, such as has been converging on gerrymandering recently, is actually quite useful for accountability. So that's why I think that's not a problem that comes up very much, but not because of explicit laws.
Other questions?
So, yeah, I have a question over here. Over here.
Oh, thanks.
One of the problems that the law involved here is related to the courts, that the court's looking for a manageable way for them to decide a question. And if you have lots of alternatives, the courts are going to say, we can't figure it out, so we're not going to get involved, because they don't want to spend all their time on these cases. They want the lower courts to be able to decide them cleanly. And so you're outlining a lot of alternatives. And I think that the alternative you outline that's most accessible is the one that says you have to throw away real outliers that we can
Great, because
easily.
I think so too.
Yeah.
But so thanks for saying that. This is partly why I wanted to try to introduce language distinguishing metrics from methods. So there's a proliferation maybe of metrics, but I would like to argue that we're converging on one overarching method, and that is the method of outliers. There's powerful precedent in legal history for slogan first, details later. So for instance, the really important court case, Reynolds v. Sims, 1964, that's the case that gave us any kind of constitutional purchase on the gerrymandering problem at all by saying one person, one vote. Okay, that was the slogan that came out of Reynolds v. Sims. But it took years, and in fact, even last year, the Supreme Court clarified what that meant. Right? So that's what I mean when I say legal frameworks often start with a slogan, an aspirational slogan, and then build consensus around how to go forward with that. I think the courts are actually a really promising place to be having this conversation because they have a well-established and fairly robust way of handling expert testimony. So there are rules for this. There's something called the Daubert standard. There's a whole sequence of ways that it's set up. The bottom line is that the court respects scientific consensus. Maybe not all parts of government do. But the court has an entrenched and explicit provision that says that in order to have expert testimony deemed relevant and admissible in a case, it needs to be in tune with the scientific community. And that's why I think it's so important to be talking about this issue publicly and recruiting people to work on it, because actually the more we work on it and the more we kind of refine our ideas, the better traction it will actually have in courts.
Okay, we have a question here and then one here.
Hi. First of all, I just want to thank you for what is a refreshing, wonderful, and frankly historic talk. And yeah, amen. And two quick questions. One is, in early part of your slide, you didn't list partisanship as one of the standards by which one should shape a district, and I'm curious as to why you left that out. You left it as sort of an alternative. And the second question is, have you worked at all to pass any of your standards into laws?
We had a meeting about that today, in fact.
Can I come?
Okay, so first, to your first question, so what I listed was 6 what I called traditional districting principles. And I put that in quotes because that's actually a term of art. So those 6 are judicially recognized. The ones below that were things that individual states might want to legislate or adopt as norms, but they're not sort of nationally recognized traditional principles. For example, compactness, 37 states have some kind of rule that explicitly says districts must be compact. Only one has an actual definition that a mathematician would recognize, okay, as a working definition. But Texas tried to say, in the landmark case Lulac v. Perry, Texas tried to say, you can't tell us to make our districts compact. We don't have a law about that. And they were told by the Supreme Court, it's now become traditional. It's a traditional districting principle, whether or not you have a law in Texas. Okay, so those 6, what I was trying to argue is that those 6 have lots of deference because they're recognized as being relevant all around the country, whether or not they're individual provisions. Yeah, and then to the second half of your question, legislation. Many of you probably know 2 states have taken the power to draw and approve the plans explicitly out of the hands of legislators, and that's Arizona and California have independent, or at least bipartisan, in the case of Arizona, commissions. So that's one kind of move for which there's some momentum around the country, but it's going to be very far off indeed that all 50 states would adopt such a plan. And so for us in the MGGG working group, we made an early decision to think really hard about the litigation side of things because there's a clearer path forward there. But actually I've become really encouraged in recent months and days about the prospects for legislation. I do think there's room for that, and let's hope that while the momentum for all this national attention on gerrymandering is happening, that there's a good opportunity to put some legislation in place nationally.
Yeah, just to follow up on that, what's your view or attitude toward actually automating districting processes to take humans with an agenda out of the equation?
Right, okay, so great. I may have left that a little bit inexplicit, so thank you for the opportunity to say that explicitly. Let us never do that. I hope that I've had a few opportunities to say that redistricting is about people. And it's about people with very different power relations and with all kinds of history. It's about communities and how they function. And I don't think we want to hand oversight of that over to an algorithm, no matter how sophisticated, no matter how nuanced, no matter how many caring people went into making it. So I think there's a really crucial role for computers to play here, but what I hope to have outlined is that it's a role putting guardrails on the process, right? And sort of bounding the latitude. The Constitution tells us that the individual states shall control the manner of their own elections. And I don't think that's the right place to be making the intervention. What I'd rather see is this community coming together to think about bounds. So several states, North Carolina, Wisconsin, the states where we're having our workshops, are all places with interesting gerrymandering histories. Their maps are so extreme that it literally wouldn't have been possible to get an extra seat in some cases. And these algorithms that I'm kind of gesturing at in this talk, no matter how imperfect they are, they're going to rein in a lot of those most extreme abuses, and I think that'll be very healthy. If you try to game these algorithms, which you'll do whenever there's a high-stakes algorithm, people will try to game it. But just by gaming these algorithms, you'll be making the situation better, and that's the best kind of intervention I think we can hope to make.
A question back here.
Yes. Are there posters or PDFs available advertising the Voting Rights Data Institute this summer?
Well, there's this website, gerrydata.org, but if folks here would like, so we are the metric geometry and gerrymandering group is really just it's innermost core, just a group of friends who thought this was really important and wanted to bring our skills to bear. And then there are sort of circles of more people around the country with all kinds of skills who want to help out. If you would like to make us posters, I say yes, sir, thank you.
Okay, thank you.
Yeah, we'll be in touch.
Up here.
Moon, is there a sample curricula available for, let's say, if I were interested in developing an undergraduate course on the mathematics of gerrymandering and redistricting?
Why, in fact, there is. If you go to tinyurl.com/teachjerry, you will find a wealth of materials handouts, lecture ideas, and if you want to come and have like incredible teachers show you how that might play out in a classroom, San Francisco, March 15th to 18th, we'll be doing teacher training and working those materials through. So yes, that's something we really, another big place that we can all, many of us, make an intervention is in our classrooms. And I think this is an incredible, there's so much fun math in it at all levels. And it lends itself really nicely to very engaging courses. I got into this in the first place by teaching a class at Tufts on voting and realizing that the geometry of voting districts could use an update. So I think teaching is a great place to be sort of working this out, and students find it really engaging. So yes, I want to encourage you to check out those teaching materials and come to our training if you can.
Thank you, Moon. You're an inspiration to me.
Oh, thanks.
Back here and then up here.
Hi, so I was wondering if proportionality could ever show up as an outlier, since clearly the distribution is not centered on proportionality. So have you found instances in which it shows up such that proportionality is actually an outlier?
So you may have heard of this thing called the efficiency gap, perhaps. So it's this formula for gerrymandering. It's supposed to be a one-stop shop for how to tell whether you've been gerrymandered. That was developed by a really smart political scientist named Eric McGee, who teamed up with a law professor named Nick Stephanopoulos. And what their score does is just that. It looks at, the bottom line is that it looks at proportionality, but with a wrinkle. Instead of perfect proportionality, the efficiency gap is oriented around a slope of 2. It says that for every additional percentage point of the vote you get, you should get 2 percentage points of the seats. And there's a whole argument for why you might think that that's reasonable or unreasonable. But however you measure proportionality, what you can do, and this is why I talk about this ensemble approach as a method and not a metric, take your favorite metric, maybe it's efficiency gap, or some other measure of proportionality, take your ensemble of maps and score them all against that metric. And that produces for you a histogram, and so you can indeed ask, is this map a proportionality outlier? It gives you a kind of meta tool, right, that you can use to evaluate along any axis that you might care about and see how extreme a particular map is. Does that make sense?
Right, thank you.
Thank you for a very interesting lecture. You, of course, have stayed away from the biggest gerrymandering, which is the Electoral College.
Ah, yes.
And how we can deal with that one.
Let's talk for a second about the Electoral College. So as I mentioned before, when I was trying to talk about why the US is the place for gerrymandering, in most other countries, in many other countries, either there's an explicitly proportional system in the legislature, or there are relatively immutable boundaries. So like, we don't change the outlines of our states very much. I mean, maybe I think Michigan and Wisconsin like to fight over the UP, but we don't actually change the boundaries of our states very often. Those are fairly stable. And that means the Electoral College, however much you might love or hate it, isn't subject to gerrymandering, right? Because there aren't people redrawing the lines to get some very specific outcome, except for 2 states. So Maine and Nebraska. We are really attached to gerrymandering. We just really like it. And so both Maine and Nebraska actually subdivide themselves into smaller pieces and apportion electoral votes to each piece. But other than that, the Electoral College is a fascinating, historical artifact that gives us all kinds of surprising. I'm determined not to. Okay. Outcomes, and it is something that there's some energy behind the ideas about changing, but it's a bit of an orthogonal fight.
And our final question?
You've mentioned that other measures like the efficiency gap or other non-geometric measures could also be considered or explored. But in terms of their viability for being considered by courts in litigation, could you compare how much emphasis is given to different types of measures? Yeah. Okay. Great. So something really interesting just happened a few days ago in this North Carolina case. So let me tell you about it. It's a good place to end the conversation. So there were not 1 but 2 cases in North Carolina that were separately conceived, separately strategized with different sets of witnesses. The League of Women Voters
filed one case, League of Women Voters v. Rucho, and the other was Common Cause. And League of Women Voters was organized around the efficiency gap, and Common Cause around computer sampling, with Jonathan Mattingly as the star witness. And when the decision came down, maybe like me, many of you got that alert pop up on some device a few days ago that said, North Carolina's maps have been thrown out. And maybe you thought, oh great, and I thought, oh my God, which case? What happened in the end, which I think is really interesting, is that the two cases were fused and the decision was a joint decision for both of those cases. And what it said was, collectively, the totality of the evidence is extremely persuasive. Okay, so efficiency gap is on the table, computer sampling is on the table. Collectively, we are persuaded. And that's really exciting. The Pennsylvania case, actually the first case of all to have computational experts on both sides, who are speaking at our conferences and on both sides, which is interesting. Something similar happened. Lots of different kinds of evidence were presented. There was some MCMC in the mix and some other kinds of algorithms. And what the court said was, collectively, we like it. What the courts aren't doing is endorsing or enshrining a particular metric or a very detailed implementation. But what they're doing instead is giving us broad strokes that say, this whole idea of understanding the world of possibilities, that sounds right. That sounds like the kind of thing you need to do to come up with an idea of who's harmed by partisan gerrymandering and how much, right? And that's been the missing piece for over 30 years in American jurisprudence on partisan gerrymandering. So we're in a really exciting moment, and the courts are saying all of the above. And when we get this decision down from the Supreme Court pretty soon, I will count it as a big win if it involves the word outlier. Slogan first, details later. Okay, all right, so thank you very much.
Yes, Moon will be up here for a few minutes if you have other questions, but let's give her a big round of applause for a most excellent talk.
Thanks, Deanna. Oh, good.